This is the 7th lecture of the course MTH 204A for section B. In the last two lectures, we have seen a lot of examples of group actions. In some of those examples, we have noticed that the concerned set X is equipped with some structure, and every element G of the acting group, the map that it yields, that is sending each X of X to GX, preserves that given structure. For example, if we consider the action of a group G on itself by conjugation, then for each G in G, we obtain the map X goes to GX G inverse for every X in G. This is an automorphism of G. Similarly, if we consider the action of GLV on V, where V is a vector space, the standard action I mean, or the action of G on the function space associated with the given action of G on a set X, we see that every element of the acting group yields a linear automorphism of the concerned vector space. Another example, if we just regard Rn as the topological space for now, then in the action of GLN R or in the action of any subgroup of GLN R on Rn, we see that every element from the group produces a homeomorphism. So by a homeomorphism, I mean a continuous bijective map whose inverse is also continuous. So every element of the acting group produces a homeomorphism of Rn. So here we have just regarded, we have just focused on the topological structure of Rn. So every G from the active group is giving a homeomorphism of this topological space Rn. Similar thing we can also observe if we consider the action of Z modulo 2Z on Sn. Recall that here, corresponding to the element 1 bar, the map that it produces, that is from Sn to Sn, is sending each x to minus x, is easily seen to be a homeomorphism of Sn. In this lecture, we will explore the following three particular instances of this general phenomenon which we are discussing. So the first one is a measure theoretic. The first one is a measure theoretic one. My suggestion for you is the following: that if you are not familiar with measure theory yet, you may skip this for now. When you will be comfortable with measure theory, you should come back and understand this. So here we are having a measure space, a set, sigma algebra and a measure, and a group G is acting on X in such a way that for any G, the map X goes to Gx is measurable. So by a measurable map, I mean inverse image of any measurable subset is measurable. Further, I assume that the action is measure preserving, that is, if we take any measurable set and consider any of its translates, then the measure is always going to remain same. So I would like to leave the following exercise in this context: that if the action of G on X is measurable, then for every integrable function and any G, these two integrals would be same. So what is this? So for any G, we have this map from X to X, sending each X to Gx, and then f is a function from X to C. So this is nothing but the composition of these two. So the exercise says that the integral is not going to be integral is going to be same for a integral is going to be same for any G. As a special case of this, we obtain something which is already familiar to us. So if we take our measure space to be X to be n and B to be the power set of n and mu to be the counting measure. So what is a counting measure? So for any set A, it just counts the number of elements of A. So that is, if n is finite, A is finite and having n number of elements, so mu A is n. Otherwise, it will be infinity. So it's so mu is a measure on n, and then what is the function space? So function space is the space of all complex sequences, and for this measure space, L1 is nothing but the collection of all complex sequences such that the corresponding series is absolutely convergent. Now now we consider we let the symmetric group of n act on n. Okay, act on n. So it's easy to see that because for any sigma and a have the same number of elements. So the action of a on and the action of the symmetric group of n on n is in fact measure preserving. Hence, as it follows from this that if we have a sequence whose corresponding series is absolutely convergent, then under any rearrangement of terms of the sequence, the sum does not change. This is because in this case the sum integral in this when the measure is the counting measure, then integral is nothing but the sum. So thus we have proved that for an absolutely convergent series, the sum does not change under any rearrangement of terms. So this is what you have seen earlier. We obtain that as a consequence of this general result. All right. So let's get back to our main content. So in view of this, it follows that if f is integrable, then for any g, gf is also integrable. So then for any g, gs is also integrable. This is because if you remember that integrability here means that this is finite. So therefore, if we consider this function, then from here we obtain that this is same as integral of mod f. So thus we obtain that since this is finite, this will also be finite. So hence if f is integrable, then gf is integrable. So in other words, we see that this subset of Lx, so Lx is the space of all functions, then L1 is a subset of that. In fact, it will be a subspace. So this is invariant under the action of G. Hence G has a natural action on the L1 space of X, of this measure space. The following exercise shows that this is not only this holds for L1, it holds for any LP. So remember that LP is the collection of all functions, such the measurable functions, such that this is finite. So again from this it follows that if f is in LP, then certainly G or GF is also in LP. So thus LP has a natural action of G. Furthermore, we see that again the main point is this, that in this action, that is in the action of G on LP, so for any small g in capital G compose F, G not compose GF and F, they have the same norm. Again, let me tell you that I am considering the action of G on LP for any given P. So thus it shows that for each G, the map that we obtain is actually an isometry because it is preserving the norm. So this, okay, so yeah, so this is easy. This can be shown as a vector space. So I assume that so if you have not seen that the LP spaces are the vector spaces, then if you have not seen, then I think you will see them very soon in your analysis course. So LP spaces are vector spaces, and in fact not only vector spaces, they are norm linear spaces, and because of the completeness with respect to that norm, LP norm, these are Banach spaces. So in this action of G on LP, on this Banach space LP, so each G, the map that we obtain is of course a linear map, and it preserves the norm. Therefore each in this action of G on LP, each small g, the map that it yields is an isometry of this Banach space. So let me quickly tell you that, quickly summarize what we have discussed so far. So from the measure preserving action of G on X, we obtain the action of G on every LP. So LP is a Banach space, and for each G, the map, the operator on LP that it yields is the operator is a linear operator preserving the norm, hence it's an isometry. So thus G acts on LP by isometries. It's always so this is for any, this holds for any P. Now among these LPs, the P equal to, among these LPs, if we consider the case P equal to 2, so LP, I mean, for any given P, LP is always a Banach space. But if P equal to 2, it is something even further. It's a Hilbert space. So it's a Hilbert space. So Hilbert space is a complete, by definition, it's a complete inner product space. So when we consider P equal to 2, then the map that each group element G produces is in fact unitary. So when P equal to 2, then the map that we obtain from L2 to L2, sending each F to GF for any given G, is unitary because of the following: that if we take two functions, then the inner product of GF1 and GF2 is same as the inner product of F1 and F2. So thus each G acts, thus for each G, the map that we are going to get is a unitary operator on this L2 space. So therefore, in general, G acts on LPs by isometries, and in case of P equal to 2, we see that G acts on L2 by unitary operators. So for this action of G on L2, the permutation representation. So permutation representation is in fact a homomorphism from G to this unitary group. So what is this? This is the group of all unitary operators on this L2 space. So for this action of G on L2, the permutation representation is a homomorphism from G to this unitary group of this Hilbert space. So let me summarize. So if G acts on a measure space in a measure preserving way, then from that we obtain that G acts on any LP by isometries, and in the very particular case when P equal to 2, in fact G acts on the Hilbert space L2 by unitary operators. Again, let me tell you that if you are not familiar with measure theory or LP spaces yet, then you may skip this example and come back to it when you will learn measure theory. However, nevertheless, this is a quite important one. And I'm sure that in your analysis course you will be introduced to these notions like LP spaces, Banach spaces, Hilbert spaces. So once you make yourself comfortable with that, then you can come back and revisit this. So we move to the second one. The second one is, of course, relevant to our course, and because this is entirely algebraic. So the second one, is of much more interest to us right now. So here we are having two groups H and K acts on H. Assume that this action is by automorphisms, that is for each K in K, the map ascending each H to KH is an automorphism of H. So in other words, we have a homomorphism from sigma from K to aught H. So if we are given a sigma, then we will see that we can construct a new group from this given H and K. So our underlying set is going to be the Cartesian product of H and K. We define the following binary operation. So for two pairs, for two pairs H1 K1 and H2 K2, so we define the binary operation as follows. So first consider sigma K1. Sigma K1 is an automorphism of H. Then we apply sigma K1 on H2, that gives us an element inside H. So we take the product of H and that. So this is going to be our first component. The second component is the obvious one, that is we multiply K1 and K2. It is a routine verification that with respect to this operation, this set becomes a group whose identity element is the identity 1H and 1K, and for any H and K the inverse is this. It's a routine verification. This is called the semi-direct product of H and K with respect to sigma. Note that sigma, it is necessary to mention sigma because it features right in the definition. Therefore, we must, whenever we say semi-direct product, we must say with respect to which homomorphism, and that also appears in the notation. So regarding the notation, please note that it is not just Cartesian product. So the one, for H we have H and K. So K to aught H we have the homomorphism. So we will close. So we will close the in the notation. We will close this cross on the side of K and keep the side keep the other side open. So yeah, so this is what we have to be careful always whenever we are mentioning semi-direct product, because HK and KH, they are certainly going to be different. So we have to be careful. Of course, when there is no danger of confusion, we can drop sigma from the notation and we can simply denote by this. However, even here we have to be careful that which side we are closing. I would like to make the following remark here, that if this sigma here, we are starting here is trivial, then automatically we see that this is nothing but H1, H2, right? Because sigma K1, since sigma is trivial, sigma K1 is the trivial automorphism. So this is nothing but H2. So first component thus becomes H1, H2. The second one becomes K1, K2. So therefore, this is exactly, that is on H cross K. If we recall that H1 K1 and H2 K2, so it is H1 H2 and K1 K2. This is exactly the group structure of the direct product of H and K. So that's what we see is the semi-direct product is actually a generalization of the direct product of two groups. So let me just again repeat that on this H cross K, we are going to define a new binary operation which will make it a group. So of course the obvious choice for on H cross K is taking component wise product, that gives us direct product. But here we are giving something else which turns out to be generalizing the notion of direct product. So this is what we call the semi-direct product. Okay, so now we have the following things which I want to leave to you as exercises. That is, inside this semi-direct product, we have H tilde and K tilde defined like this. Inside semi-direct product, these are the subgroups. We have these two subgroups. And it's quite easy to see that H is isomorphic to H tilde. We do have a canonical map HK, similarly for K tilde. So these are the basically copies of H and K inside this H semi-direct product K, and the copy of H is normal. So it's very natural to ask what happens to the copy of K. So this is what is said by the third exercise, that copy of K is normal if and only if sigma is trivial, and sigma is trivial is same as saying that semi-direct product is nothing but the direct product. So for the semi-direct product H and K, the copy of H is always normal. The copy of K cannot be normal unless the semi-direct product becomes the direct product. As an immediate corollary for this, we observe the following, that following that if sigma is non-trivial, then H semi-direct product K with respect to sigma cannot be abelian, even both H and K are abelian, because for an abelian group any subgroup has to be normal. So if sigma is non-trivial, then certainly this copy of K cannot be normal. That shows that H semi-direct product K cannot be abelian. So thus we see that using semi-direct product we can construct a non-abelian group from two given abelian groups. We will do that quite often later on. In fact, when we will construct a non-abelian group of order p cube from zp square and from z modulo p square z and z modulo pz. So we will construct a non-abelian group of order p cube using semi-direct product. So the way to make the semi-direct product non-abelian is choosing a non-trivial homomorphism. In particular, for any abelian group H, we do if we consider I to be the unique homomorphism from Z modulo 2Z to odd H, it's there. We have already seen that on any abelian group we do have an action of Z modulo 2Z, and this group element 1 bar, the automorphism of H that it gives is sending each H to its inverse. So we have a unique homomorphism from Z modulo 2Z to odd H, and with respect to that new unique homomorphism, if we consider the group H and consider the semi-direct product with H and Z modulo 2Z, it has to be non-abelian. Exercises: if we take H to be Z modulo NZ, then identify this group. Let me tell you that this group we have already seen. And another exercise is for Z modulo 3Z and Z modulo 4Z. What is Z modulo 3Z? What is the automorphism group of Z modulo 3Z? This is nothing but isomorphic to Z modulo 2Z. So we do have a unique non-trivial homomorphism from Z modulo 4Z to Z modulo 2Z. And with respect to that unique homomorphism, non-trivial homomorphism, if we consider the semi-direct product, then so what's the order of semi-direct product of H and K? So since the underlying set is H Cartesian product, so the order of the semi-direct product is the product of the order of H and order of K. Therefore this is having a group of order, this is a group of order 12, and earlier we have seen it's a non-abelian group, of course, because the unique non-trivial homomorphism. We have already seen two non-abelian groups of order 12. One was D12, another one was D4, A4. Now I leave this to you to check that indeed the semi-direct product is going to be not isomorphic to either D12 or A4. So thus we construct a different, again in the sense of isomorphism, a different group of order 12. Now let me talk about some standard examples of semi-direct product. So the first one is by the linear action of GLV on V. Then this is the semi-direct product which we obtain. So this semi-direct product, so a typical element V comma A, if we send it to T V comma TA, we see that this establishes an isomorphism between this semi-direct product and the group of all affine invertible linear transformations on V. In particular, when V is finite dimensional, then finite dimensional real linear product space, then we can consider the subgroup of all orthogonal operators on V, and then let phi to be the restriction of this I, restriction of this I. Here again, so what is I here? So from GLV to, so if GLV in this action, what is for this action, what is for this action, what's the permutation presentation? It indeed becomes a map from GLV to GLV, and what is that map? This is nothing but an identity map. So here I stands for the identity, this identity. So if you restrict the so from GLV to GLV, if we restrict this to if this column restrict this to O, then this semi-direct product we obtain. And like earlier we see that this semi-direct product is nothing but isomorphic to the group of all isometries of this real inner product space V. The second one is indeed a generalization of the previous one. So here suppose a group and a subgroup of its automorphism group are given. So here that we what we obtain is from A is here. So from A to aught G, we have this natural inclusion, let's call that I. So with this natural inclusion, if we consider the semi-direct product, then we can consider the semi-direct product. It is called the relative holomorph of G with respect to A, and denoted by this. And as we have done earlier, we can show that this relative holomorph is isomorphic to the following subgroup. That is the subgroup of all which consists of all permutations of G of this form, that is automorphism followed by a translation. So for all the permutations of G of this form, they form a subgroup of SG, and H and this relative holomorph is isomorphic to that subgroup. So that is why I am so if you see that if you see that this nothing but putting this in the general form. Hence we see that just like earlier we proved that this holomorph, which is defined as the semi-direct product, is actually isomorphic to the group of all maps of this form. And as a special case of this, we see that we obtain this semi-direct products that we have considered earlier. So this we can immediately see that these are nothing but special cases of holomorphs. So the second one is basically a generalization of the previous one to any general group. Before we move ahead, let me tell you something. So for any subgroup A of automorphism group of G, the copy of G inside the holomorph is easily seen to be this, and it has to be normal. So it has to be normal because of the general consideration. When A is whole aught G, then we call it the holomorph of G. Okay, let's come to the third example of semi-direct product. So this one is I'm just mentioning for your general knowledge, and I won't use it further. So here the situation is slightly more complicated, that here we are given two groups and a set, and one of these groups H is acting on the set X. Now we consider the collection of all functions from X to G. For example, earlier we have considered a collection of all functions from X to C, and that was and with respect to pointers addition and scalar multiplication, it was a vector space over C. Now here we consider only set of all maps from X to G, and with respect to pointwise multiplication defined as defined below, it forms a group. So this G is denoted by Gx is a group. And now we are going to define an action of action of H on Gx. Remember that H already acts on X. So how is that defined? It's defined in the most natural manner, that for any H and F, HF is defined like this. And like earlier, not only I leave this to you to check. Not only this defines an action, also this action of H on Gx is by automorphism. This is because of the multiplication in Gx is defined pointwise. So this object is called the Ret product of G with H. So this I just mentioned, as I have already said, for your general knowledge. Henceforth, this object will not appear most probably. Now we should talk about the semi-direct products more. So it's customary for getting to given H and K and homomorphism phi from K to H, it's customary to identify H with H tilde. So like I was telling that this is nothing but we do have a canonical isomorphism from between H and H tilde and K tilde. So it is a customary to identify H with H tilde and K with K tilde by this canonical isomorphism. So after this identification, the previous conditions look like this. So now H is a normal subgroup of G. So here G is the semi-direct product. I think I should maybe I should make that change here. So instead of saying this, let me just write phi k. So here G, this is the semi-direct product. This is the semi-direct product. H is a normal subgroup of the semi-direct product of H and K. And then the most desired one, that is after this simplification, we see that phi k upon H is nothing but KH, conjugation of H by K. So let me again repeat the point that I want to make. So in the definition of semi-direct product, you see this kind of objects are coming, because that's how the semi-direct product is defined. So in the beginning, an object of this type was very suspicious, but once I make the necessary identification, now this object turns out to be just the conjugation of H by K inside the semi-direct product. Okay. It is now natural to ask when a given group can be recognized to be isomorphic to the semi-direct product of two of its proper subgroups. So for any given G, we want to ask if there exists. We want to ask whether we will be able to write G as the semi-direct product of H and K for two proper subgroups H and K and some homomorphism from K to H. This is very natural to ask. Then only we will be able to decompose a given group into semi-direct product. So that question is being answered by the following recognition theorem. So it says that given any group G, if H and K are two subgroups of the following properties, that is H is, first of all, H is normal. Next is the intersection is to be trivial, and the third one is G is the product of H. G can be written as the product of H and K. Then there is a homomorphism from K to H such that G is isomorphic to H semi-direct product K with respect to this phi. So the proof from this is quite straightforward. Recall that for any G, Ig denotes the map which is the inner conjugation by G, sending each x to Gx G inverse. And since H is normal, so if we restrict Ig to H, then that gives a automorphism of H. That's exactly what we are considering here. So for each K, we restrict phi K to H, and that gives us a homomorphism, and the rest is direct verification. Hence I would simply leave that to you. So now let me introduce a terminology for our convenience. So for a group G and a subgroup H, a subgroup K is said to be a complement of H if G can be written as a linear combination of H and K. G can be written as a product of H and K, and their intersection is trivial. So with this terminology, we see that in order to obtain a given group as the semi-direct product of two of its non-trivial subgroups, what we have to do in view of this recognition theorem is we have to find a non-trivial normal subgroup which is having a we have to find a non-trivial normal subgroup which is having a complementary subgroup. Okay, because if H is a non-trivial, which is having a non-trivial complementary subgroup, because if H is a non-trivial subgroup, normal subgroup having a non-trivial complementary subgroup, then in view of this recognition theorem, we will see that G will be isomorphic to the semi-direct product of two of its proper subgroups. This is what, in view of the recognition theorem, we have to do if we want to break a given group as the semi-direct product of two of its proper subgroups. But note that this is not always possible because first of all, not all groups possess such normal subgroups. One easy example for that is if the group is simple, then certainly it is not going to be a normal subgroup, non-trivial normal subgroup which will admit a non-trivial complementary subgroup. Even if the group is not simple, still it is not true. See the following exercise. This is the group of quaternions. So I leave this to you to prove that this cannot be written as the semi-direct product of two of its subgroups, non-trivial subgroups. Remember that for any group G, of course, you can write G as G semi-direct product, the trivial subgroup. But so this trivial decomposition is always there. Hence, we will always. So from now on, for our purpose, we will only look for when H and K both will be proper. All right. So now let us talk about some applications of this recognition theorem. So the first application is we can write Sn as the semi-direct product of An, and for any transposition tau, let this be the subgroup generated by tau. So Sn is isomorphic to this semi-direct product. For D2n, the decomposition is even more natural because D2n is basically generated by two things, Rn rho, and D2n is isomorphic to the subgroups generated by Rn rho. And like earlier we have observed that this AGLV is isomorphic, is a affine general linear group, is isomorphic to the semi-direct product of these two subgroups. So this part is actually isomorphic to V. Similarly, the group of all isometries is, in fact, we can recognize that as the semi-direct product, as this semi-direct product. Here I would like to leave the following exercise to you, that if H, can I write A4 as the semi-direct product of two non-trivial subgroups of A4, namely H and K. Okay. Now let's come to the third instance, the third situation of the phenomenon that which I said that we will study in this lecture. So here the situation is G acts on a vector space by linear automorphisms. So first let's observe that G acts on V by linear automorphisms. That is exactly same as saying G has a representation on G have a representation on V. So when G does thus representation of G on a vector space V is same as saying the G acts on that vector space by linear automorphisms. Now I will give some common examples of representations. So again, let me remind you that representation is nothing but is nothing other than action of a group G on a vector space by linear automorphism. So thus, to begin with, representation is a special case of group actions. So the first example is the most trivial one, that is it sends every group element to the corresponding identity of the vector identity operator of the vector space V. This is called the trivial representation of G on V. More generally, if we are given a homomorphism from G to the multiplicative group of F, then that yields a representation of G on any vector space V in the following way. This is easy to see because rho G1, G2, if you see, that's nothing but chi G1, G2, I. So this is nothing but chi G1 into chi G2, I. So thus you see that this trivial representation is nothing but a special case of this when chi is identically 1. In fact, if dimension of V is 1, then all representations of G on V will be necessarily of this form. That is, if dimension V is 1, then any representation of G on V has to be given by some chi, which is a homomorphism from G to the multiplicative group of F. This is because of when G has dimension on, what is GL is isomorphic to this multiplicative group of F. Okay, that forces therefore this is now clear. In particular, we obtain that for any n in n, the only representations of Sn on C are the trivial one and the sign representation. Remember, the sign representation sends each sigma to sign sigma. Okay, so it's a map from Sn to plus minus 1. So of course this is a subgroup of the multiplicative group. Okay, so in view of this, we see all representations of Sn on C are so these are all the representations. Here the case for Rn I would like to leave to you as an exercise. Now let's move to the second one. So here the acting group is Z modulo Nz. For fix any k from 0 up to n minus 1. Then and define chi k to be the following homomorphisms, sending the class of m to e to the power 2 pi I k m for every m. So it's easy to see that chi k is a homomorphism. So the homomorphism, thus for each k from 1 up to n minus 1, for each k we obtain a representation of Z modulo Nz on C. And it's also easy to see that all representations of Z modulo Nz on C are precisely the ones given by the chi case. That is, if you consider any arbitrary representation of Z modulo Nz on C, it has to be some chi k. That is quite clear. So this is what we obtain as a special case of this. Another standard example of a representation that we have already seen is the permutation representation associated to any given action. In particular, the left and right regular representation of any group are of course the representations of that group on the vector space LG. And another example is the representation of Sn on Cn. So where each sigma is being sent to this permutation matrix. The next example is about a representation of D to N. So we send R to this 2 by 2 matrix and row to this 2 by 2 matrix, it's easy to see that this defines a homomorphism from D2n to D2n to GL2C, and consequently we obtain a representation of D2n on C2. So for each k we thus obtain a representation. Of course all of them are not going to be different, that's a separate thing. The next example is about a representation of this quaternion group. So the quaternion group, so if we send plus minus 1 to I2, plus minus I to this, j to this and k to this, that gives us a representation of Q8 on C2. The advantage of considering this representation is that, well, before that you can observe that this assignment is indeed a homomorphism from G to GL to C, which is also injective. Therefore, thus now you can consider Q8 to be the subgroup consisting of these 8 concrete matrices. So the advantage of considering this representation is, if you see that the group Q8 is defined in an abstract manner, in an artificial way. So, but after considering this representation, we now see that Q8 is no longer anything something abstract. It's the concrete group of concrete matrices, and operation is usual matrix multiplication. Thus, by means of representation, we are able to see every element by some concrete matrix. In fact, this is the main point of considering representations of groups. A group is an object which is abstractly defined. The elements are also abstract objects. So now once we consider a representation of a group, then that means we let the linear automorphisms of some vector space to stand for the group elements. Thus now we can regard the group elements as certain linear maps. Then we can use techniques from linear algebra to do something, and then we come back and say something important regarding the structure of the group. So alone, by staying inside the group, this may not be possible because elements are abstractly defined. We don't have any idea about what these elements are and how they behave. But after considering a representation, since then things become concrete, we can really do that. And of course, we can use the techniques in this large branch called linear algebra. All right. So the next example is also of the same spirit. Here we consider the Klein-4 group, which is also quite abstractly defined. But once we consider that, once we observe that this is nothing but isomorphic to Z modulo to Z direct. So instead of this, maybe for now I should put this. So this is the usual direct product. When the groups are abelian, it's customary to say the direct product as a direct sum, but we'll come to that later. So the Klein-4 group has this following representation, and thus if we wish, from now on we can simply consider Klein-4 group to this following group of concrete matrices. Now I would like to leave some the exercises for you. So you will see that these exercises are the analogs of what we have seen in general group actions. The first one is if you are having a group action and if W is a G-invariant subspace, that is for any G, rho GW, any W, rho GW is in W. Then we see that restricting all the linear maps to W, we said that they are also each such restriction also becomes a linear automorphism of W. Hence, we obtain a representation of G on W. This is called a sub-representation of the given row on W. A special case of that we see when X is a finite set and G acts on X. then the one dimensional subspace generated by this vector is G invariant, and therefore G has a natural action on this subspace. In fact, we see that this action is in fact the trivial representation of G on that subspace. When n is a natural number 3, n is a natural number which is at least 3, then in the action of Sn on Cn, we also see that this complex hyperplane is invariant under the action of Sn, because if we permute the coordinates of any point here, then the same equation is going to be satisfied. Thus Sn acts on this complex hyperplane. So whenever we are dealing with algebraic objects, then after sub-objects we should look for the quotient objects. That's also done here. So here let W be a G invariant subspace, then define rho bar G to be this. So it's easy to verify that rho bar G is a linear operator on this quotient space, and in fact this is an invertible linear operator. Thus sending each G to rho bar G is a representation of G on the vector space on this quotient space. This is called the quotient representation of G of rho defined by W. Then of course we can consider products. So if we are given k number of representations, we can then consider their products, which is defined in the most natural way. As a special case, we see that if we fix d number of integers in 1 up to n, then one has the following representation of z modulo nz on CD on this d-dimensional complex space. That's quite obvious. And then we come to the fourth. Then we come to the fourth one. So the fourth exercise says that if we for a given representation of G on a vector space V, if we are given a normal subgroup of G, okay, let me again start. So just a minute. Yeah. So here we are given a vector space over F and a normal subgroup of n of G. Now for every representation of this quotient group, if we compose this, so the situation is suppose we are having a representation on representation rho of G modulo n, then if we compose that with pi, then we get a representation of G on the, so from the representation of G modulo n, we obtain the representation of G. That's just simply composition. And in fact, from what we have seen earlier, for any representation of G, if n is contained in the kernel of rho, then certainly this factors through G modulo n, right? So this factors through that. So thus what we have seen is for any representation rho whose kernel contains n, then rho for a rho has to be of this above form. So again, let me repeat that if rho is a representation whose kernel contains n, then we see that rho must be the composition of this quotient map and some representation of G modulo n on the same vector space. So thus we see that the representations of this quotient group G modulo n and the representations of G which has n contained inside the kernel are thus in a bijective correspondence. So again, let me repeat, from G, for any G representation of G modulo n, if we compose that with pi, then we get a representation of G, And the second thing is, if a representation of G has n contained in its kernel, then since this factors to that, so therefore we see that the given representation of G is basically the composition of a representation of G modulo n with pi. So thus the representations of G having n inside the kernel, and the representations of G modular in bijective correspondence. As a particular case, a very special case of that, we see that any one dimension, we see that any representation of G on F, it has to be of this form chi hat, where chi is a representation of G modulo G prime. So this is because of if the multiplicative group is abelian, so automatically we will see that any homomorphism must factor through some homomorphism of G modulo G prime to F naught, and therefore from as a special case of this general observation, we see that all representations of G on F are obtained by composing pi, the quotient map from G to G modulo G prime, with all the representations of G modulo G prime on F. Okay, or equivalently all the homomorphisms, because we are talking about only representations on AF. So the representations on F or homomorphisms from G to the multiplicative group of F are all the same thing, which we have already seen. Okay, so with that I will finish this lecture. So basically here our objective of this lecture was to study the phenomenon when a group is acting on a set, or the set has some structure, and the maps that every group element yields preserves that given structure. We consider three special instances. The first one was for measure theory. The second one was the action of a group on another group by automorphisms, which leads us to SemiDirect product. And the third one is about linear actions of groups, which is basically representations. And then we have seen several examples of representations. Okay, so with that I will stop.